Welcome to catenation. Today we will discuss very important chapter p block elements. Modern periodic table contains 7 periods, 18 groups, 4 blocks. Name of the 4 blocks S, P, D, F. S and P collectively called as main group or representative elements. D block called as transition elements. F block called as inner transition elements. Why S and P alone called as main group or representative elements? Because S block contains highly electropositive alkali metals. P block contains highly electronegative halogens. So both of them collectively called as main group or representative elements. D block acts as a bridge between S and P, so it is called as transition elements. F block form the series within the transition elements, so it is called as inner transition elements. S block occupied group 1 and 2, D block occupied group number 3 to 12, P block occupied group number 13 to 18. Group 13 contains boron, aluminium, gallium, indium, thallium. Group 14 contains carbon, silicon, germanium, tin, lead. Group 15 contains nitrogen, phosphorus, arsenic, stibine, bismuth. Group 16 contains oxygen, sulfur, selenium, tellurium and polonium. Group 17 contains fluorine, chlorine, bromine, iodine, astadine. Group 18 contains helium, neon, argon, krypton, xenon, radon. Group 13 called as boron family. Group 14 called as carbon family. Group 15 called as nitrogen family. Group 16 called as chalcogens or ore forming elements. Group 17 called as halogens or salt producers. Group 18 called as noble gases. I will repeat again. Group 13 called as boron family, 14 carbon family, nitrogen family, chalcogens, halogens, noble gases. P block contains all the 3 different kind of elements: metals, non-metals and semi-metals. Example, in group 14, this boron is semi-metal, rest of the metal. This zigzag row occupied only semi-metals or metalloids. From the zigzag row, left hand side only metals, right hand side only non-metals. General electronic configuration of group 13, Ns2 Np1, group 14 Ns2 Np2, group 15 Ns2 Np3, group 16 Ns2 Np4, group 17 Ns2 Np5, group 18 Ns2 Np6, completely filled orbital. Now, general characteristics of p block elements. First point, general electronic configuration of p block elements. What's the general electronic configuration of p block elements? We can write Ns2 Np126. Next, p block contains all the 3 different types of elements: metals, non-metals and semi-metals. P block contains metals, non-metals and semi-metals are metalloids. Generally, ionization potential moving from left to right increases. So, p block elements has higher ionization potential compared to the other group elements. P block elements has higher ionization energy. Then next one is inner pair effect. Moving down the group, less availability of ns electron for formation of bond. This effect is called as inner pair effect due to poor shielding effect of d and f orbital. These second period elements maximum covalent bond only for due to absence of d orbital. Example, boron can form only the maximum covalent bond only 4. So the net charge of the sphere will be 1 minus. But third period element, aluminium can form more than 4. It can utilize d orbital also. We can write hexafluoridoaluminate. Hybridization sp3d2. Hybridization of second period elements, this one will be sp3 tetrahedral. Next one will be octahedral. Geometry octahedral. This one tetrahedral. Then another important property, second period elements can form p pi multiple bond. Example, carbon can form p pi multiple bond with carbon or other elements with oxygen, with nitrogen, oxygen p pi multiple bond, nitrogen p pi multiple bond. So second period elements can form p pi multiple bond. Heavier element can form d pi or d pi only. So I will repeat the characteristics of p block elements. General electronic configuration ns2 np126. P block contains metals, non-metals and metalloids. P block has higher ionization potential when compared to the other block elements. The P block has inner pair effect. What's the inner pair effect? Less availability of ns electron for formation of bond due to poor shielding effect of d and f orbital. These second period elements maximum covalent bond only 4, but third period onwards they can expand more than 4, even 6 also they form due to presence of d orbital. But second period cannot exceed more than 4 due to absence of d orbital. Second period elements, they can form multiple bond. What type of multiple bond? P pi multiple bond. But heavier elements cannot form p pi. They can form only d pi or d pi multiple bond. Next we will discuss properties of group 13, boron family. What are the elements are there in the boron family? Boron, aluminium, gallium, indium, thallium. These are the elements occupied in group 13. Group 13, boron, aluminium, gallium, indium, thallium. Symbol of boron B, Al, Ga, In, Tl. Atomic number 5, aluminium 13, gallium 31, indium 49, thallium 81. Electronic configuration: boron, helium followed by 2s2, 2p1. Aluminium, neon followed by 3s2, 3p1. gallium, argon followed by 3d10, 4s2, 4p1. Indium, xenon followed by 4d10, 5s2, 5p1. In thallium, xenon followed by 4f14, 5d10, 6s2, 6p1. So in the electronic configuration, boron and aluminum having noble gas core, gallium and indium noble gas plus 10d electrons, but thallium having noble gas plus 14f electrons and 10d electrons. This F and D has poor shielding effect. So this Ns electron, 6s electron do not involved in the formation of bond because nucleus firmly attract the outermost electron. That is why thallium shows more inner pair effect. This inner pair effect increases moving down the group. Next one is atomic size. Generally moving down the group, size of atom increases due to introducing extra cells, right? So boron will be lesser than aluminum. Aluminum expected lesser than gallium, but here some deviations are there. The atomic size, while writing atomic size of group 13, boron lesser than aluminum, but aluminum greater than gallium, gallium lesser than indium, indium lesser than thallium. Here aluminum and gallium deviations are there. Atomic size of aluminum 143 picometer. Atomic size of gallium 135 picometer. The reason is gallium has d orbital. It has poor shielding effect. So it attracts the electron more firmly, the size of atom decreases. So generally moving down the group, we expected atomic size should be increases, but deviations are there. Aluminum and gallium, the reason is poor shielding effect of d orbital. Next one is ionization energy. The definition of ionization energy, amount of energy required to remove electron from outermost orbit of the gaseous atom to form cation. This ionization energy inversely proportional to atomic size. Ionization energy of the atom inversely proportional to atomic size. So atomic size of group 13 we already discussed. Boron lesser than aluminum, aluminum greater than gallium, gallium lesser than indium, indium lesser than thallium. From this we can write ionization energy of group 13. Boron should be greater than aluminum, aluminum should be lesser than gallium, gallium should be greater than indium, indium greater than thallium. So moving down the group, we expected ionization potential should be decreases, but here deviations are there. Aluminum and gallium, same reason we can say due to poor shielding effect of d orbital, attract the electron more firmly, so more amount of energy required. Remove electron from the outermost orbit of the gallium when compared to the aluminum. Next one is electronegativity. What's the definition of electronegativity? The tendency of atom attract the shared pair of electrons towards itself in a molecule. The electronegativity of group 13 we can write like this. Boron is 2, Aluminium is 1.5, gallium is 1.6, indium 1.7, thallium 1.8. So boron to aluminium, it will be decreases. From aluminium to thallium gradually increases. Here also shielding effect acts as an important role. Moving down the group, due to d and f orbital poor shielding effect, it attracts the electron more firmly. That is why moving down the group increase the electronegativity. Next is physical property of group 13 elements. Boron is the very hard metal, very hard element. So it has high melting point when compared to its own group elements. Boron has high melting point because very hard in nature, but other elements, rest of the group 13 elements are soft in nature and they have low melting point. They have low melting point. Gallium has very low melting point, 29.7 degrees Celsius. So gallium exists liquid at room temperature, but it has high boiling point, very low melting point. Boiling point of gallium is 2676 Kelvin. So which is used to measure higher temperatures because of high boiling point. Density, moving down the group, density gradually increases. So density of boron lesser than aluminium, aluminium lesser than gallium, gallium lesser than indium, indium lesser than thallium. In group 13, moving down the group, density will be increases. In group 13, the first element boron, it's a very less abundant element in the earth crust. It contains only 0.001% by mass in the earth crust. Boron obtained in the form of boric acid, H3BO3, borax, Na2B4O7.10H2O, and kernite, Na2B4O7.7H2O. Boric acid, borax, and kernite. These are the minerals of boron. Boron has two different isotopes, B10 and B11. B10 isotope 19%, B11 isotope 81%. Next element is aluminium. Aluminium is the most abundant metal in the earth crust. Most abundant metal and third most abundant element. Third most abundant element in the earth crust. Percentage of aluminium is 8.3% by mass in the earth crust. Aluminium obtained in the form of bauxite. Molecular formula of bauxite, Al2O3.2H2O, and cryolite. Molecular formula Na3Al F6. Both bauxite and cryolite called as minerals of aluminium. But aluminium extracted only from bauxite, so bauxite is called as ore of aluminium. Aluminium is the lightweight, high tensile metal, so it used for making aircrafts. Next, gallium, indium, thallium, they are less abundant element in the earth crust. Less abundant elements in the earth crust. Next is chemical properties. Chemical properties of elements depends on its oxidation state. In group 13, boron, aluminium, gallium, indium, thallium. Due to small size, boron is very compact compared to the other group 13 elements. So it has more ionization potential. We cannot remove 3 electrons from outermost orbit. So boron do not form +3 oxidation state. But aluminium can form +3 oxidation state. Aluminium and other metal, they can form +3 oxidation state. Heavier elements can form +1 oxidation state also. Gallium, indium and thallium, they can form +1 oxidation state. Due to inner pair effect, moving down the group, increase the stability of +1 oxidation state. Stability of +1 oxidation state moving down the group increases. Stability of +1 oxidation state. Aluminium lesser than gallium, lesser than indium, lesser than thallium. Moving down the group, +1 oxidation state increases due to inner pair effect. So thallium can form 2 different types of halides, TlCl and TlCl3. Which one has more ionic character among these two? Thallium chloride, TlCl greater than TlCl3, because covalent character directly proportional to oxidation state. In TlCl3, oxidation state of thallium is 3+. In TlCl, oxidation state of thallium is 1+. So lower oxidation state predominantly ionic character, higher oxidation state predominantly covalent character. Next one is boron when combined with the halogen to form trihalides. These trihalides electron deficient in nature. Example, boron combined with chlorine. Its outermost 3 electrons are there, mutually sharing 1 electron with 3 chlorine atoms. Chlorine outermost 7 electrons are there, but boron outermost only 3 electrons are there. So chlorine required 1 electron to reach octet configuration. So mutually sharing 1 electron between 3 chlorine atom to form 3 covalent bond. After formation of molecule also, boron outermost has only 6 electrons. It sort of 2 electron from octet configuration. So this compound is called as electron deficient compound. This electron deficient compound ready to accept electron from electron donor. So it is called as Lewis acid. So BCl3 or BF3 readily bonded with ammonia, because nitrogen contains 1 lone pair of electron to form coordination bond between boron and boron trichloride and ammonia. This bond is called as covalent coordination bond. Here ammonia acts as a Lewis base, BCl3 acts as a Lewis acid. This bond is called as coordination bond. Next, aluminium chloride achieve the stability through formation of dimer. In dimer, between the 2 aluminium atoms, 2 chlorine act as a bridge. So it has 4 terminal chlorine atoms, 2 bridge chlorine atoms. Distance between aluminium and chlorine in the bridge chlorine 221 picometer. In the terminal chlorine and aluminium 206 picometer. So aluminium achieve the stability through formation of dimer. Next is anomalous properties of boron. Boron differ from its own group elements. What is the reason? Because it has a very small size, so higher ionization potential, absence of d orbital and high electronegativity. That is why boron shows different property from its own group elements. The reason behind anomalous property of boron. First one, small size, so higher ionization energy, absence of d orbital, higher electronegativity. These are the reason behind boron shows a different property from its own group elements. Few anomalous property of boron. The covalent bond of boron cannot exceed more than 4 due to absence of d orbital. But third period element like aluminium can form more than 4. It can form coordination bond 6 also. Name of the compound tetrafluoridoborate 3, tetrafluoridoaluminate 3. It is sp3 hybridization. This one sp3 d2 hybridization. BCl3 only form covalent in nature. Boron will form only covalent compound, but other element from group 13 they can form both covalent as well as ionic compound. Boron very hard in nature. Very hard in nature. It has high melting point. It has very high melting point. But other elements, aluminium, gallium, indium, thallium, they have low melting point. So anomalous property of boron. The property of boron differ from its own group elements. The main reason, small size, higher ionization potential, absence of d orbital, higher electronegativity. Few anomalous property, covalent bond cannot exceed more than 4. Other element can form 6 also. Boron will form only covalent compound. Other metal halide they can form covalent as well as ionic compound. Boron very hard in nature, high melting point. Other elements from group 13 they have low melting point. A reaction between group 13 elements and air. Reaction with air. Generally crystalline boron do not react with air at ordinary temperature. No reaction at room temperature. Even aluminium also, to form thin layer on the surface of the metal, it is called as protective layer, which prevent the further affection of air. But they react with air at high temperature. Not only aluminium, boron, aluminium, gallium, indium, thallium, they react with oxygen at high temperature to form corresponding oxides. Boron with oxygen to form B2O3. Similarly, aluminium will form Al2O3, Ga2O3, indium oxide In2O3, thallium oxide Tl2O3. It is unbalanced equation. We can take 4 boron 3O2 2B2O3. Nature of the oxides. Boron will form acidic oxide. It is acidic in nature. Aluminium and gallium oxide called as amphoteric oxide. The meaning of amphoteric oxide, it can be act as both acid as well as base. Indium and thallium will form basic oxides. So moving down the group, metallic character increases. That is why boron will form acidic oxide, both aluminium and gallium will form amphoteric oxide, indium and thallium will form basic oxide. These elements readily combine with nitrogen to form nitride at high temperature. We can write general formula En. Group 13 combine with oxygen and nitrogen at high temperature to form corresponding oxide and nitride. Next chemical property is reaction between group 13 acids and alkalis. Reaction with acids and alkalis. Boron do not react with acid or base at ordinary temperature. No reaction will take place between boron, between acid and base. And aluminium can be dissolved in acid to form corresponding salt with hydrochloric acid to form aluminium chloride and liberate hydrogen gas. 2Al, 2Al3, so 6HCl, 3H2. And aluminium also react with base to form corresponding salt, sodium meta-aluminate, in aqueous solution to form coordination compound. To NaAl OH 4 times, it will carry 1 minus plus 6H2. Name of the compound sodium tetrahydroxo aluminate 3. Generally, metals do not react with the base, but aluminium can be react acid as well as base to give corresponding salt and liberate hydrogen gas. So nature of aluminium is called as amphoteric in nature. So name of the metal, amphoteric metal. That is why aluminium can produce salt with both acid as well as base. Next chemical property is group 13 with halogens. Reaction with halogens. Generally, group 13 elements readily combine with the halogens to form trihalides EX3. The X is considered as fluorine, chlorine, bromine and iodine. So all the group 13 elements combine with fluorine, chlorine, bromine, iodine to form trihalides except thallium triiodide, because during formation of bond do not produce sufficient amount of energy, remove electron from ns orbital, because in the thallium ns orbital strongly bound with nucleus due to inner pair effect. So thallium triiodide alone do not form, but rest of the other elements combine with other halogens to form corresponding salt. Example, boron with fluorine to form boron trifluoride. Similarly, aluminium with fluorine to form aluminum fluoride AlF3. Gallium with fluorine to form gallium fluoride. Indium with fluorine to form indium fluoride. Thallium with fluorine to form thallium fluoride. Now arrange the increasing order of covalent character. Generally, covalent character inversely proportional to size of cations. According to Fajan rule, decrease the size of cation, covalent character increases. It can polarize more. So which is the compact one among the following in the cation? Boron smaller than aluminium, aluminium greater than gallium. So based on this we can arrange the covalent character. Generally these trihalides covalent in nature. BF3 form only covalent character, but these elements to form both covalent as well as ionic in nature. When compared to the TlF3 and TlF will be more ionic in nature. TlF3 more covalent in nature. Next is some important compounds of boron. The first compound is borax. Molecular formula of borax Na2B4O7.10H2O, decahydrated molecule. Reaction with water. Action with water. When borax dissolve in water to form alkali solution and boric acid Na2B4O7 when dissolved in water to form sodium hydroxide. 2 sodium is there in the reactant side, so we can write 2NaOH. And boric acid, molecular formula of boric acid H3BO3. Number of boron in the reactant side 4 is there, so we can write 4 molecule of boric acid. Now total number of hydrogen in the product side 4 into 3 12, 12 plus 2 14, so we can write 7 molecule of water. When borax dissolve in water to form sodium hydroxide alkali solution and boric acid. Here sodium hydroxide stronger than boric acid is a weak acid, so which is considered as basic in nature. Borax is basic in nature. Next, action of heat on borax. Molecular formula of borax Na2B4O7.10H2O. While heating, first it will become anhydrous. It lost 10 molecule of water. It will become Na2B4O7. Further increase the temperature, we will get sodium metaborate. Molecular formula sodium metaborate 2NaBO2. Total number of oxygen in the reactant side 7 oxygens are there. Here only 4 oxygen, remaining 2 boron with 3 oxygen to form boric oxide. Name of the compound sodium metaborate. And boric oxide. Molecular formula of borax is Na2B4O7.10H2O. When dissolved in water to form alkali solution, strong alkali, sodium hydroxide, weak acid, boric acid. So nature of the borax is basic in nature. While heating, first it will become anhydrous compound. Further increase the temperature, it will become sodium metaborate and boric oxide. Next compound of boron is boric acid. Molecular formula of boric acid H3BO3. First one is preparation of boric acid. Preparation of boric acid from borax. Molecular formula of borax Na2B4O7 treated with hydrochloric acid, aqueous solution of acid. This 2 sodium combined with the chlorine to form sodium chloride. So we can write 2NaCl plus boric acid H3BO3. Number of boron 4 is there, so we can write 4 molecule of boric acid. 2 chlorine is there, so we can take 2 molecule of hydrochloric acid. Total number of hydrogen in the product side 4 into 3 12 is there. Already 2 hydrogen, so 5 H2O. Borax plus 2 molecule of hydrochloric acid and 5 molecule of water to form sodium chloride and boric acid. Boric acid is weak monobasic acid. Basicity is 1. Weak monobasic acid. When boric acid dissolve in water to form tetrahydroxyborate compound plus hydronium ion H3O plus. Next is action of heat on boric acid. Action of heat on boric acid H3BO3. Molecular formula of boric acid H3BO3 heated at 370 Kelvin occur in dehydration. We will get orthoboric acid. Molecular formula of orthoboric acid HbO2. Now 2 molecule of orthoboric acid 2HbO2 further increase the temperature above 370 Kelvin. It lose another molecule of water. It will become boric oxide B2O3. Next is structure of boric acid. In boric acid, boron has sp3 hybridization. This boron bonded with 3 oxygen atoms. This oxygen bonded with hydrogen atoms. This dotted line called as intermolecular hydrogen bonding. Intermolecular hydrogen bonding. The another compound of boron is diborane. Molecular formula of diborane B2H6. Preparation of diborane from boron trifluoride. When boron trifluoride react with lithium aluminum hydride, we will get diborane B2H6 plus lithium combined with fluorine to form LiF. Similarly, aluminium combined with fluorine to form AlF3. It's an unbalanced equation. 4BF3, 3 lithium fluoride. So 2B2H6. Total number of hydrogen, 12 hydrogens are there. Here also 12 hydrogens are there. 3 lithium fluoride, 3 aluminium, 3 AlF3. Total number of fluorine 12. Here also 12 fluorine is there. So preparation of diborane from boron trifluoride when treated with lithium aluminum hydride to form diborane. This boron trifluoride react with the sodium hydride. Again we will get diborane B2H6. So 2 boron is required. 6 hydrogen, 6 NaF. The 6 fluorine combine with 6 sodium to form 6 sodium fluoride. Diborane from sodium borohydride and iodine. These 2 iodine combine with 2 Na to form 2 sodium iodide. 2 boron is there. B2, number of hydrogen, 8 hydrogens are there in the reactant side. So B2H6 plus H2. When sodium borohydride react with the iodine to form sodium iodide, diborane and hydrogen. So these are the 3 different method of preparation of diborane. BF3, boron trifluoride with lithium aluminum hydride, boron trifluoride with sodium hydride, sodium borohydride plus iodine to form sodium iodide, diborane and hydrogen. Next is a structure of diborane. It is one of the dimer. These 2 boron connected with 2 bridge hydrogen atoms. It has 4 terminal hydrogen atoms. So boron contains 2 bridge hydrogen atoms, 4 terminal hydrogen atoms. These 4 terminal hydrogen atoms are two center, 2 electron bond. 2 centers, 2 electron bond. These 2 bridge hydrogen atom as hydrogen atom has 3 center, 2 electron bond. This diborane, a toxic gas, when spontaneously react with air to form boric oxide B2O3 and water. 6 hydrogen is there, so 3H2O. Total number of oxygen in the product side 3 plus 3 6, so 3O2. Diborane is a toxic gas. It spontaneously react with the air to form boric oxide and water. When react with water, diborane react with water to form boric acid. Molecular formula of boric acid H3BO3. Number of boron is 2 in the reactant side, so we can write 2 molecule of boric acid. Total number of hydrogen in the reactant side 6 hydrogens are there. Total number of oxygen 6 oxygen, so we can write 6 molecule of water plus 6H2. When diborane react with water, air to form boric oxide, with water to form boric acid. It react with Lewis base. When diborane react with Lewis base to form bond cleave product B2H6. It's one of the dimer I already said. When react with trimethylamine, 2 molecule of trimethylamine, this nitrogen has lone pair, so it acts as Lewis base. This diborane considered as Lewis acid. Dimer break down into monomer to bonded with trimethylamine to form coordination compound. So we discussed general characteristics of p block elements and group 13. In next video we will discuss group 14 elements. Thanks for watching.